Hi, I'm Matt, head of Brain Interfaces Electrical Engineering. Our fully implantable N1 device depends on a battery for continuous operation. When that battery is running low, charging is accomplished through wireless power transfer. However, unlike many consumer electronic devices, which can simply offer a physical connector, charging a fully implantable device poses several unique challenges. First, the system must operate over a wide charging volume without relying on magnets for perfect alignment. The system must be robust to disturbance and complete quickly so as not to be overly burdensome. However, most important is safety. In contact with brain tissue, the outer surface of the implant must not rise more than 2 degrees C. In pursuit of these goals, our charging system has gone through several engineering iterations. The first, if you watched our pig demo in August of 2020, Gertrude was implanted with a version of the N1 charged with our first generation charger. This device was implemented in a small puck package and later separated into a remote coil and battery base. This charger was challenging to use. However, we learned a lot through its implementation. Our current production charger, which charges our current generation of implants, is implemented in an aluminum battery base, which also includes the drive circuitry. A remote coil 4 times the size of our original device, also disconnectable. This remote coil has increased switching frequency, driving improved coil coupling. This charger is in use today, including several applications within our engineering and animal test facilities. I'd like to show you one of these applications here with a device we call our simple charger. And the coil has been embedded into the habitat. With the addition of one new outer control loop plus a banana smoothie pump, the troop has been trained to charge themselves. So let's see how Pager charges his implant. On the right, we're streaming real-time diagnostics from Pager's N1. When he climbs up and sits below the coil, you can see the charger automatically detect his presence and transition from searching to charging. We see the regulated power output on a scale of 0 to 1 and the current driven into his battery. I mentioned earlier that we improved the coil coupling. However, the high quality factor coils exhibit good charging performance over relatively larger distances, but as they're brought closer to the implant, what you see is a peak splitting effect, where the best, highest efficiency power transfer is pushed up into higher frequencies outside of the ISM band, required for compliance with regulated radiated emissions. In our next generation charger, we address this problem by the introduction of dynamic tuning, shown on the right. This allows us to, in real time, adjust the resonant frequency of the transmit and receive coils so that we can change their properties just ahead of degraded performance. The electrical engineering team is currently engaged in developing a 3rd generation charger. Notable improvements include bidirectional near-field communication.